So last section in 9.2, we did significance tests for a population proportion. In 9.3, we're going to do similar stuff. We're still going to make inferences and do some significance testing, but it's going to be for a population mean mu. So for starters, what are the three conditions we have to meet to be able to conduct a significance test for a population mean? Well, two of them are going to be the exact same as for proportions. So we still have to trust that the data were collected randomly, right? So the data have to come from either a random survey or experiment, and the independence condition is still there. And remember, if we're sampling without replacements, we have to mention something about the 10% condition. So those two are the exact same. The only one that's different is the normality condition. So if you'll remember for means, there is one way we can say that the sampling distribution is approximately normal, and that is if the sample size is big enough. So if n is greater than or equal to 30, then we can mention something about the CLT being met, put a check mark, and be on our way. But if you have a small sample size, we have to sort of find a way around that, right? So the other way would be if we had a sample size of less than 30, which is exactly what the example in these notes uses. So if you have a sample size that is less than 30, hopefully you have that data set, right? There's not going to be very many data points if it's under 30. So hopefully you have that data set. You're going to have to look at the graph of the sample data and provide some evidence, right? So you might have to construct a little graph yourself, like a dot plot, for example, and report back and say, look, I didn't see any strong skew, I didn't see any outliers, so I wasn't overly offended by this graph. We're going to go ahead and make the assumption that this sample data came from a normal parent population. So this is only done if you have a small sample size and you're actually given the data points that you can graph. Or maybe they've already given you a graph of the sample data. If the sample size is big enough, we don't even have to worry about that at all, right? So there's two routes here to meet that normality condition. So the next part here says, what test statistics do we use when testing a population mean? Is the formula on the formula sheet? So you'll probably recognize this from last semester when we did confidence intervals, right? We don't actually use z-scores typically for means. We use t-scores. So I just noted here, this is the realistic case, right? Sigma is unknown. We don't know what the population standard deviation is. If we knew that, they wouldn't really pay us very much money to make inferences, right? They would already know everything they needed to know. So for all practical purposes, we're going to use t-scores when it comes to means. And to get the t-score, we take our sample data, our sample mean, whatever that is, and subtract mu naught, which is just the mu from the null hypothesis, divided by the sample standard deviation over the square root of n. So little s with the subscript x, that's the sample standard deviation. In fact, that's the reason we have to use a t-score, not a z-score, because we don't know sigma, we don't know the population standard deviation. We have to rely on just the sample standard deviation. And the other really important thing that you're going to have to mention that's unique to the t-distributions, you have to say what the degrees of freedom are, right? So you always have to mention, for means, when you use a t-test statistic, what degrees of freedom did you use? And that's a really simple formula, right? It's just one less than the sample size, n minus 1. So this is the realistic formula, right, the practical one that we'll use to get our test statistic. It's going to be a t-score, and here's how you calculate it. And just to be thorough, the unrealistic one, like the case where you would actually use z-scores, would be the same formula, except you would have sigma instead of the sample standard deviation. Neither one of these, by the way, is on the formula sheet. There is something that refers to test statistics, right? If you remember from the previous notes, they do give you a test statistic equation, but it's more general. These two formulas, neither one is on the actual formula sheet. Okay, and then scrolling down here, how do you calculate p-values using the t-distributions? So we've actually calculated probabilities with t-distributions before. So don't forget, you got to use degrees of freedom, right? So that's something you always have to mention if you're using t-distributions. So what are the degrees of freedom? And there's two ways you can find this. So you can look at the t-values on the t-chart, right? You can look up your t-score that way, or if you're really calculator friendly, you can use the tcdf command in the calculator. So both of those we've actually had experience with. So just as a really brief example, right? So let's say we get a test statistic. Our t-score is down here, right? Maybe it's like negative 2.5 or something. And then we're going to be looking for the probability in this shaded region. So what is that area? Or if you look at the t-chart, that's called a tail probability. So either you get that value from the t-chart or you use the tcdf command. And the tcdf command is kind of like normal CDF, it's just the inputs are a little bit different. So when you make the technology statement, you have to note the lower bound, which in this case over here would be negative infinity, right? Negative 1e99. The upper bound, which would be whatever this boundary's at. And then don't forget the degrees of freedom. And I'm happy to see people use the calculator. Just to plug for the AP scoring here, you have to have those labels, right? Don't just put numbers in there and expect the grader to know what that means. So label what you use for the lower bound, the upper bound, and the degrees of freedom. All right, so let's get to the lone example for these notes. It says, Abby and Raquel like to eat sub sandwiches, don't we all? However, they notice that the lengths of the 6-inch sub, quote unquote, sandwiches they get at their favorite restaurant seem shorter than the advertised length. So these are a couple really observant students. To investigate, they randomly selected 24 different times during the next month and ordered a 6-inch sub, as they call it. Here are the actual lengths of each of the 24 sandwiches in inches. So these two students actually went out, got some hands-on data. They picked random times to order these subs, and they got 24 subs. Looks like they just marked each sub to the nearest quarter of an inch. And they were nice enough to put these in order if you look, right? 4.5 was the shortest one. And then reading from left to right there, 7.00 was the longest one. Okay, so part A. Do these data provide convincing evidence at the alpha equals 0.1 level that the sandwiches at this restaurant are shorter than advertised on average? And that on average part is actually kind of key here, right? Even if they advertise a 6-inch sub, I mean, it's reasonable to expect that you might get one that's a little bit shorter, one that's a little bit longer. But if we get like on average, we get a big enough sample set to say, look, on average, these things aren't even 6 inches, right? I understand a little bit of variability, but now you're just lying. So to prove or disprove anything along those lines, when it says convincing evidence, that's our indication that we need to run a hypothesis test. And now that we've got some experience in doing these, to do this well and to receive full credit, we've got to follow that 4-step process. So let's give an introduction here. We have to start with the state step. So what are our hypotheses going to be? We want to test the null, which the null would say everything's fair, there's no difference, so the safe bet would be the true mean is just 6 inches. And then the alternative, what these two students are worried about is this restaurant shorting people? Are they not giving them the food that they're advertising? So is the true mean actually less than 6 inches? Okay, so these are good for the hypotheses. There's two other components for the state step that we still need to point out. The first one being, what exactly is mu here, right? We have to describe that. We have to say what it is in context. So mu is going to be the true mean length measured in inches for what this restaurant calls a, quote, 6-inch sub. And we'll just have to see about that. And notice I underlined this restaurant. Let's be clear about that. We're making an inference about the true mean length of the sandwiches at this restaurant, right? Not all restaurants. We're curious about understanding how they make their sandwiches. And for now, that restaurant shall remain nameless. Okay, the other thing we have to do, we have to say how picky we're going to be. Actually, it's defined for us. We just need to mention it here. And we're going to use alpha equals 0.1, right? 0.10 as our significance level. All right, so the state step is all good. We've got each of the 3 components that are necessary. I need some room here. Let's go to the plan step. So the plan step, the first thing we have to do is name the test that we're going to do, right? So this is your first experience doing that. It's called a one-sample t-test for the mean, mu. So if the conditions are met, we'll go through and check each one in a second. We'll do a one-sample t-test for mu. Okay, the first condition we can knock out, typically we just say random and it's somewhere in the problem, right? And this problem's a little bit different, but it says they randomly selected 24 different times when they ordered the subs. So that's good. We're going to assume that makes a random sample in this case. So the order times were random, so the sample should be random here. That gets a check mark. Next, the independence condition. So they definitely sampled without replacement here, but they only sampled 24 subs, so that should be way less than 10% of all subs made at this restaurant in a month, right? Further, we could just say this restaurant makes way more than 10 times the sample size. So 10 times 24 would be 240. Right, that's a really safe bet in this case. This restaurant makes far more than just 240 subs in a month, so the 10% condition is met here. Check mark. All right, and then I just need a little bit more room here. Let's talk about the normality condition. The normality condition. So a thought that comes to mind, it would be nice, it would be quick, it would be easy if we could just say something about the central limit theorem, put a check mark and move on. But unfortunately, that's not the case. You can only use that when the sample size is bigger than 30, right? So we've got a small sample size here, meaning we're going to have to actually provide some evidence. We're going to have to actually plot the data. So don't think you can just slide by with the central limit theorem, right? CLT is not going to fly here. The sample size is too small. But we've actually got the data points. And they're going to be easy to make a dot plot with because they're measured by the quarter inch. So let's start with a dot plot. I think the shortest one here is 4.5. And it goes all the way up to 7.0. And I've got to put some marks in between those two. So we have to make some sort of graph. I guess if you really wanted to, you could make a histogram or a normal probability plot. Seems like it would be really easy to just make a dot plot here, though. Ooh, and I can't forget to label. These are the sub-lengths in inches. So then we can actually just go down the line here, right? We've got 4.5, a couple 4.75s, a few 5.0s, 6 5.5s, so on and so forth until you get all 24 dots on there. The biggest one is 7.00. All right, and once you get your dot plot made, we just have to take a moment and comment about this. It's definitely not perfectly normal. It's not perfect by any means, but you shouldn't expect it to be perfect because there are only 24 dots on this graph. but you can kind of start to visualize where a normal curve might have fit over that if there weren't holes and such within it. But the point being is, this doesn't really offend us as far as like, it's not skewed, and there aren't any obvious outliers, right? There's no outliers. So when we summarize this, we take our evidence here, we made a dot plot. So now we can say the sample data really doesn't have any strong skew, and it doesn't have any outliers. So, it doesn't really offend us. So we're going to go ahead and trust that it came from normal parents. In this case, it's going to be safe for us to use the t-distribution. So this thing passes the test. No strong skew, no outliers. We're going to go ahead and say it's safe to use the t-distribution in the next step. Which is the do step. It's time to actually do some statistics. And there are two things we need here. One of those being the test statistic. Actually, the first one has got to be the test statistic. So that's our t-score. So if you'll recall, it's the sample mean minus mu naught over s sub x over the square root of n. Don't forget mu naught is just the mean mu from the null hypothesis. All right, so it's time to plug in values, right? We're going to crunch these numbers. We're going to get this t-score. And it turns out, well, we're not given x bar, nor are we given the sample standard deviation. So we don't know what the sample mean is, and we don't know what the sample standard deviation is. The good news is we have the sample data, right? So we can actually calculate those, and we don't even have to calculate them by hand. So if you can just throw the data into L1, right, you've got the 24 data points. If you can put those in a list in your calculator, put those in L1, then we can do 1 var stats to get the sample mean and the sample standard deviation. So I've got my calculator here. I can go to stat, edit. That means I'm going to edit a list. And then I've actually already got the data entered in L1. So if you look, I've already got my 24 spots filled. I've got everything typed in. So once you do that, you can go to stat, right? Stats right here, stat, calculate, 1 var stats, stands for 1 variable statistics, right? And then make sure it's just set to L1 for your list, right? That's when we just put all the stuff into. Hit enter a couple times until it says calculate. There you go. Your sample mean is 5.677. The sample standard deviation, 0.657. So let's get those numbers down here. Our sample mean, the mean of these 24 data points, is 5.67 inches. And then the standard deviation of this sample, right, these 24 sub-sandwiches, would be 0.657 inches. Okay, so now we're ready to calculate our t-score for our test statistic. So sample mean, we just found that, 5.67. The mu naught value, that's 6 inches from the null hypothesis. And then we know what S is, and we know what N is. Which, in your calculator, be careful with the parentheses in the denominator here, gets us negative 2.461 for our t-score. So there's our test statistic. Negative 2.461 is equal to t. Okay, so we need that t-score to now find the other thing, the p-value. So the thing we're suspicious about, what's the probability we would get a sample mean this low if the true population mean were actually 6 inches, right? In other words, what's the probability we get a t-score at or below negative 2.461? And that comes from this thought right here. It's my little thought bubble. What's the probability we would actually get a sample mean less than or equal to 5.67 inches if this restaurant was telling the truth and the true mean was supposed to be 6 inches? Okay, and to answer that question, you can either use the t-chart or what I'm going to use, the tcdf command. So what is this probability? That gives us our p-value. So we can say using technology, the command tcdf, that's what we're going to use. lower bound, the numbers below this would be negative infinity, so negative 1e99, which should be the default in your calculator, by the way. The upper bound would be negative 2.461. And the degrees of freedom, which I'm going to put a little star on because you have to mention that. Don't forget to mention degrees of freedom. Would be 1 less than 24, which is 23. And that should give you a p-value of 0.011. Okay, so if the p-value is 0.011, we got that from the tcdf command, you should probably have a pretty good idea right now as to whether you're going to reject or fail to reject the null. So now time for the last step, the conclude step. So first we have to make the right decision, and I'm actually going to leave some blanks here. So we have to say, because our p-value of blank is blank, then alpha equal to 0.1, we blank. That's the decision. So hopefully you're experienced enough by now. Right? I know we've shown a couple memes in class, right? We have a couple different ways to remember this. Our p-value is definitely lower than alpha in this case. So if our p-value is low, we reject the null hypothesis. So because our p-value of 0.011 is certainly less than alpha, which is just 0.1, we reject the null hypothesis. So that's the correct decision, and then you can't forget to leave out the context statement that follows this. So this makes perfect statistical sense. Can you explain what that means in the context of the problem? Well, basically, from the sample that these two students gathered, we have convincing evidence that the so-called 6-inch subs at this restaurant are actually less than 6 inches in length on average. So although it might be normal to expect a little bit of variation in the sub length, what we found was convincing evidence that the actual mean, right, the true average mean length for these sandwiches is below 6 inches. So both of these parts are critical. You have to make the correct decision, of course, and then you have to give a context statement, right? The conclude step, you have to summarize your decision in context. All right, let's get to part B, the last part here. It says, given your conclusion in part A, which kind of mistake, a type 1 or a type 2 error, could you have made? And explain what this mistake would mean in context. Well, we rejected the null hypothesis, right? So since we rejected, there's only one of these that we could have made. Remember, type 2 is failed to reject, and we didn't fail to reject here. So we definitely would fall into the type 1 category, right? So since we rejected the null, we run the risk of having made a type 1 error. I'm not necessarily saying that we made one, but the risk is there. So what does that mean? We might have made a type 1 error. What does that mean in the context of this setting? Okay, so if we were mistaken, right? A type 1 error would be like concluding that the average sublength for this restaurant, like the one they call 6-inch subs, is less than 6 inches. Basically, accusing the restaurant of selling subs that are less than 6 inches on average, when in reality they were, equal to 6 inches or maybe even bigger than 6 inches. So a type 1 error in this case would be accusing the restaurant of selling short sandwiches, when in reality the sandwiches were just fine in length. Heck, they might even been a little bit bigger on average. We might have just gotten a bad sample. Notice that I didn't use the word reject. I didn't mention anything about HNO or HO or HA. So the context statement just describes the situation, right, in terms of the problem. It doesn't use a lot of heavy stats, definitions, or notation. Anyway, that's our first exposure to significance tests for means. Don't forget we use t-scores for these. That is all for these notes. I'll see you in class.